Welcome to the first of 4 videos on the final topic of the AS Further Maths 1 course, and that's on elastic collisions in one dimension, which is all based in chapter 4. The first examples here are very straightforward, really just getting used to the idea of finding the coefficient of restitution and using its equation, and we'll come to that in more detail with the examples in a moment. So we use E to be the coefficient of restitution, and E varies between 0 and 1. Where E is 0, you have a perfectly inelastic collision, and when E is 1, you have a perfectly elastic collision, and we'll talk more about that through the examples. But the basic equation here, as you can see, is to find E, you find the speed of separation, and you divide by the speed of approach. So in example 1, it's just literally some very simple examples to understand how we use the formula, and again, setting out as we did with our momentum and impulse chapter, I tend to just put the before speeds directly above the particles and the after below, just to tidy things up and save a load of diagrams. So in part 1, the speed immediately before the impact, we have A has a speed of 8 meters per second, and we're told that B is at rest. And after the impact, we have that A is at rest, and we have that B is travelling with a speed of 2 meters per second. So to find the coefficient of restitution, E, the speed of separation is the separation of the particles after the collision, immediately after the collision. So you can see there 2 take away 0 will just be 2. So that is our speed of separation. And the speed of approach, the difference between the two speeds there, you can see is going to be 8. So our coefficient of restitution for the first example is 1/4. And then parts B and C. Part B, before the impact, A is moving with a speed of 6 and B is moving with a speed of 3 in the given directions. After the impact, A continues with a speed of 4 and B continues with a speed of 5. So again, the speed of separation is the difference between those two speeds there, which will be 1, and the speed of approach was 3. So the difference between the speeds immediately before the collision. So again, we have that E equals 1/3. And then in part C, the reason I'm going through all of the examples is that we have speeds in different directions. So A is travelling with a speed of 11 meters per second before the impact, and B is travelling with a speed of 7. After the impact, A is reversed with a speed of 6 and B is reversed with a speed of 3. So it's important to note when we are going in different directions, then obviously the speed of separation is going to be 3 plus 6, which is 9. Okay? Sometimes it could be read in the equation as 3 minus 6, but it's much easier to look at the fact that the speed of separation, if B is travelling with that speed of 3, A is travelling with that speed of 6, then they are separating with a speed of 9 meters per second. Similarly, when you've got a head-on collision, obviously that's approaching with a speed of 11, that's approaching with a speed of 7, so our speed of approach there is 18. So in this case, our speed of separation is simply 1/2. So moving on to examples number 2 and 3. In example 2, here we are given the coefficient of restitution and we need to find one of the missing speeds. So it tells us that two particles A and B are travelling in the same direction on a smooth surface with a speed of 4 and 3 meters per second respectively. They collide directly and immediately after the collision continue to travel at the same direction with speeds 2 and V. So A is continuing to travel with a speed of 2 and B is what we need to find out. So if I just put velocity of B there. Now we're told that the coefficient of restitution between the particles is 1/3. So in this case, we can still use our coefficient of restitution equation. So E is the speed of separation. And obviously in this case, we know it's going in that direction. But again, our answer will always refer to the direction that we've put there. So our speed of separation is going to be VB, whatever the velocity B is, minus 2, divided by the speed of approach. And again, you can see the difference there is 1. So we know that E is 1/3. That's given to us in the equation. So that equals, well, we can just obviously write it as VB minus 2. So therefore, VB will be 7/3 meters per second, which is obviously the velocity of B, or the speed of B, immediately after the collision. And then on to example number 3. Here we have two particles A and B of masses 200 grams and 400 grams. The moment you're told about the masses, we obviously, well, we know that we're going to be using the conservation momentum as well. So here we may have two unknowns. So one equation will come from our coefficient of restitution, which you've just been taught, and one will be from chapter 1, the conservation of momentum, as we know that momentum is conserved within a collision. So we've got our two particles A and B. A is 0.2 kilograms, B is 0.4 kilograms, are travelling in opposite directions with speeds of 5 and 4 meters per second respectively, if I just note that they're particles A and B. They collide directly, and immediately after the collision the velocities are V1 and V2. So to be honest, I would put VA and VB so we can see which one relates to which without checking. Measuring the direction of motion of A before the collision, so that's why I've put them in that direction. We're told that the coefficient of restitution is 1/2. So again, as I've said already, we've got two unknowns. So one equation will be the one we've just learnt. So our coefficient of restitution is going to be the speed of separation, so that will be VB minus VA, divided by the speed of approach, and they're going in opposite directions again. So that will be a speed of approach of 9. We know that E is 1/2, so therefore we've got that 9/2 when we times by the 9 is going to equal VB minus VA. So again, we need another equation. So remembering chapter 1, if we use conservation of momentum, remembering that momentum is a vector quantity, so we must state which direction we're taking as positive. So we have the total momentum before impact is 0.2 times 5. Plus 0.4 times by minus 4, because that was travelling in the opposite direction. And that is going to equal 0.2 VA plus 0.4 VB. Now it's probably simpler just to times everything by 5, just to tidy things up a little bit possibly. So then we're going to have that 5 plus minus 8, is going to equal VA plus 2VB. So therefore we have minus 3 is going to equal VA plus 2VB. If we go back to our first equation here, we can rearrange that. So for example, VB is going to equal 9/2 plus VA. And if we substitute that to replace our velocity of B there, we know that minus 3 is going to equal VA plus 2 lots of 9/2 plus VA, because that's our velocity for B. And then we can say that minus 3 is going to equal 3 VA plus 9, so VA is going to equal minus 4. It does actually ask for the velocities in the direction of motion of A before the collision. So therefore we can leave it as minus 4, but obviously we can say that it has reversed direction after the collision. And then just going back to the first equation, we know that VB is going to equal 9/2 plus VA, which we know is minus 4. So VB equals 1/2. So again, that has also reversed direction after the collision. Now, the last example we're going to look at before you have a go at some questions is perhaps more of an exam style question. You see a lot of these in the exam. Rather than having lots of values given, you get things in terms of, for example, in this question, E and U. So it's just really testing that you're happy with your algebraic skills as well. So example number 4, we have two balls, P and Q, of masses 3m and 4m. So we have P and we have Q. We're told that they're moving in opposite directions towards each other along the same straight line. Immediately before they collide, P has speed 3u and Q has speed 2u. The coefficient of restitution is given as E between the two particles. And we need to find, first of all, show that the speed of Q, so if I just put V of Q, is going to be U over 7, and then in brackets 15E plus 1. So obviously we have our velocity of P as well. So it's our velocity of Q that we need to show first of all. But you shouldn't be put off by, the use of algebra. It's exactly the same as example 3. 2 unknowns, so 2 equations, and one is going to be conservation of momentum, and one is going to be the coefficient of restitution. So if we start with coefficient of momentum, again we have to say which direction is positive. So by now you should be used to thinking 9mu minus 8mu, because that's travelling in the opposite direction, is going to equal the momentum, as I've got the arrows after the collision, which will be 3mvp, and then plus 4mvq. Again, we can cancel out all of the m's by dividing the equation by m. And then the coefficient of restitution, we are told that the coefficient of restitution is E, so the speed of separation will be VQ minus VP, divided by the speed of approach, which will be 5u. So we've got 5eu equals VQ minus VP. Now, we were asked to find out what VQ is, so therefore if I find out what VP is from this equation, so we've got VP is going to equal VQ minus 5EU, and if we substitute that in to replace VP, we'll then have our equation with VQ. So just simplifying equation 1, we've just got U on the left-hand side is going to equal 3 lots of VP, which we now know is VQ minus 5EU plus 4VQ. So we've got that U equals 7VQ minus 15EU. So therefore we've got U plus 15EU equals 7VQ. And we can then factorise U as it's in both terms there. So 1 plus 15E all divided by 7 equals VQ, which was the answer we were asked to show. Now the second part of the question, because that was obviously the answer for part A, is giving us that the direction of P is unchanged. So just going back to the diagram there, if the direction of P is unchanged, then that tells us that the velocity of P must be greater than 0 after the collision. Now, we also know that VP is equal to the velocity of Q, which we'll state again in a moment, from our first equation, minus 5EU. So therefore VP is going to equal U over 7, 1 plus 15E minus 5EU. So we have VP equals U over 7, 1 plus 15. And if we put that over 7, then that's going to be minus 35 EU over 7. And then if you can see how we can put that together, if you've got 15 EU minus 35 EU, then that will be U over 7, 1 minus 20E. So we are told that VP has to be greater than 0. Since U has to be positive, therefore we can just concentrate on this part of the equation. So if VP is greater than 0, we know that 1 minus 20E must be greater than 0. So if 1 is greater than 20E, we therefore can state that E is less than 1/20th. However, it does state the range of possible values of E. So in an exam, if you left the answer like that as they have in the textbook, you could risk losing a mark. Because when we first introduced E, we know E varies between 0 and 1. So therefore, we can say that 0 is less than E, which is less than 1/20th, will be our range of possible values for E. And the last part of the question, part C, basically takes us back to chapter 1. It gives us that the impulse of P on Q, so the impulse of P on Q is going to equal 80 mu over 9. So if I just do another quick sketch of, if it's P on Q, we're looking at Q. So the impulse is going to be in that direction. And we know before the collision, we were travelling with a speed of 2u, and after the collision we are travelling with a speed of, just reminding myself, was u 1 plus 15e all over 7. So here we have 80 mu over 9. The impulse is obviously in that direction. So we have that 80 mu over 9 is the mass, which was 4m. V, which is travelling in the direction of motion, which is u 1 plus 15e all over 7, minus 4m times by minus 2u. So we have that 80 mu over 9 is going to equal 4mu over 7 multiplied by 1 plus 15e plus 8mu. And if you rearrange all of that, then we have that E is going to equal 1/27th. Right, that gives you enough information now to have a go at exercise 4A. So good luck with those questions, and we'll catch up again soon with the next 3 videos in this chapter.